April Simons here with the McWhorter School of Building Science at Auburn University. Today we are continuing our lectures on structures topics. Today we'll talk about beam support reactions. So we're going to walk through basically how to calculate some beam support reactions, and then we'll show some examples of real life beams and how those support reactions actually relate in the real world. So let's just start with some examples here. So basically the process for calculating support reactions of a beam is based on the premise that beams are in equilibrium. So we'll apply the three equations of equilibrium to solve for those support reactions, whatever they may be. For this particular example, we're going to start with a 3-foot long beam. We've got a 1.1 pound load in the center of that beam. And we're going to calculate the support reaction on the left side and the right side of that beam. We're starting with a simple beam here, such as short length and a small weight, so that we can relate that to something in real life later and see what that looks like. All right, so again, here we have a very simplified beam where we have a really small load of 1.1 pounds directly in the center. When we analyze any kind of structure with the assumption that it's in equilibrium, again, we use the equations. Some of the forces in the x direction are equal to 0. Some of the forces in the y direction are equal to 0. And the sum of the moments about any point on that structure or structural element, in this case, of a beam is going to be equal 0. When we deal with beams, most of the time, we don't have forces in the x direction. So most of the time, we end up using these two equations. Look at the forces in the y and some of the moments about a point. With a beam or any kind of structural element, typically we'll take the moments about one of the unknown points. So in this case, that would be the left-hand side of the beam. So we're calculating the reaction on the left-hand side of that beam, and we're also calculating the reaction on the right-hand side of that beam. So here we've got this 1.1 pound force. That force is going to be applied again at the center of the beam, so 1.5 feet from the left and 1.5 feet from the right. So 9 times out of 10 when we deal with beams, we'll start with that sum of the moment equations, take the moment about one end of the beam or the other. So here let's start with the left side. So summing the moments about the left-hand side of the beam and set that equal to 0. And as sort of a review, we typically take the approach that moments in the counterclockwise direction are positive, moments in the clockwise direction are negative. And again, it really, we could use just the opposite of that. Some textbooks use the opposite approach, but we'll take the approach that counterclockwise is positive, clockwise is negative, and as long as we're consistent, we'll come to the right answers here. So if we take the moments of all of these forces about the left-hand side, we have 1.1 pounds. So our applied force here, 1.1 pounds, times the distance to that left-hand support, which is, in this case, 1.5 feet, okay? And that is going to cause this beam to rotate about that point, okay, in a clockwise direction. So that'll be a negative moment. And then we have to look at this right-hand support. That will also produce a moment about the left-hand side. So we've got the reaction on the right, and we multiply that by the distance here of 3 feet, okay? That's going to be a counterclockwise moment, so that will be positive. And we'll set that equal to 0. So there's only 2 forces here causing a moment about the left-hand reaction. That's our applied force of 1.1 pounds and our support reaction on the right side here. So if we do the math here, we get that our support reaction on the right-hand side of that beam is going to be equal to 0.55 pounds. Okay, 0.55 pounds. Now, if we sum the forces in the y direction, summing the forces in the y equals 0, okay, we have our reaction on the left side minus our 1.5 pounds applied force plus our reaction on the right side. Set that equal to 0. And if we substitute in 0.55 pounds here, So now if we solve for this reaction force on the left, got RL is equal to 0.55 pounds. So another way to get the support reactions when we have a special case like this where we have one applied load directly in the center of the beam is to use sort of a shortcut formula. So here when we have this situation, the reaction on the left-hand side of our beam will be equal to the reaction on the right-hand side of the beam, and that's going to be equal to the load, the applied load, in this case 1.1 pounds here, divided by 2. Okay, so if you think about it, we have one load applied, and that load is directly in the center, so half of that load will be resisted by the left-hand side of the beam, whereas half of that load will be resisted by the right-hand side of the beam reaction here. So we take the load divided by 2, and we get 0.55 pounds for our support reaction, again, on the left-hand side and the right-hand side of the beam. So to illustrate how support reactions work, we have a simple 3-foot-long beam here, and we're going to hang a weight or apply a weight of exactly 1.1 pounds in the center of this beam. And so the way that it works is the two scales that you see here will read and record our support reactions. So the scales are serving as the actual supports for this particular beam. So when we hang our 1.1 pound weight in the center of this beam, which is 3 foot long, then we should get our 0.55 support reactions that we calculated earlier. So now we can see that we have 0.55 pounds for our support reaction on the left side and 0.55 pounds for the support reaction on the right side of this beam. Okay, so let's look at another beam example here where we've got 2.2 pound loading applied 1 foot from the left support, and then we have a 1.1 pound loading applied 1 foot from the right support. We still have the same 3 foot long beam, so if we show that here, we've got 1 foot from the left support. We've got a foot in between our loads here. And then we have another foot from the 1.1 pound loading to the right-hand side of the beam. So again, overall, we've got our same 3 foot long beam. We're just changing the loading conditions a little bit. So again, we'll apply our 3 equations of equilibrium here. Sum of the forces in the x direction equals 0, sum of the forces in the y equals 0, and sum of the moments about any point is equal to 0. And solve for those 2 unknown support reactions. Again, we've got one on the left-hand side and one here on the right-hand side. So to solve for the support reactions here on the left-hand and the right-hand side of this beam, we will start by taking the moments, again, about any point, but typically I'll take the moments about the left-hand support, and we can sum the forces in the y direction, set both of those equal to 0, assuming this beam is in equilibrium. So starting by taking the moments about the left-hand support, again, remembering that counterclockwise is positive, clockwise will be negative. So we have a 2.2 pound load here, which will cause this beam to rotate clockwise, so this moment will be negative. And we have 2.2 pounds times the moment arm, or the distance here between the force and the point, is 1 foot. Our next load of 1.1 pounds will also cause a clockwise moment, so this will also be negative. 1.1 pounds times the moment arm here will be 1 foot plus 1 foot, so this will be 2 feet. And then we have a support on the right-hand side, which will produce a clockwise moment, so this one will be positive. Our right-hand support reaction times the entire length of the beam, which here is 3 feet. We'll set that equal to 0. If we solve here for our right support, our R, we get 1.47 pounds. So now we can just sum the forces in the y direction and set that equal to 0 to solve for the reaction on the left-hand side. So sum of the forces in the y equals 0. So we have our RL That's positive. Since we've drawn it up, we've got 2.2 pounds, negative. We've got 1.1 pounds here, which is negative since it's acting downward, and we have our support reaction on the right, our R, all equals 0. So we'll substitute in the 1.47 pounds here for our R. And solving for our left-hand reaction, we get 1.83 pounds. A couple of things to note. First, we can't really use a good shortcut formula here since our loads are not equal. They are equally applied in terms of distance, but they're not equal in magnitude. We've got a greater load here on the left side of the beam, so those are not going to come out equal. And so since our greater load's applied on the left side of the beam, our reaction on the left side is going to be greater than our reaction on the right side, and we see that holds true here. So now we'll look at that second example where we have two loads of different magnitudes applied 1 foot from either end of the supports. So here we have 2.2 pound load that's going to be applied 1 foot from the left-hand side of the beam. And then we have 1.1 pound, which will be applied 1 foot from the right-hand side of the beam. And we can see that the support reactions we get, which is measured by the scales here, is going to be 1.83 pounds on the left side and 1.47 pounds on the right side, which matches up with what we showed in our calculations. So to summarize the process for solving for support reactions for a beam or a girder or any kind of structural element that is horizontal supporting loadings is to use our three equations of equilibrium, and that is sum of the forces in the x direction equals 0, sum of the forces in the y direction is equal to 0, and sum of the moments is equal to 0. Typically, we can eliminate that first equation, sum forces in the x, because we don't have any forces applied in the x in most cases. So we'll narrow that down to two equations typically. So we'll start with sum of the moments about one of those support reactions, and then sum of the forces in the y direction. Set those equal to 0 to solve for our support reactions.